Okay, this video goes with the mole to pressure proportionality worksheet that we're doing. And so one thing, sometimes to solve some simple gas law problems, they they want you to kind of figure out how many atmospheres of gas you could get from some other gas or something. Well, anyway, if you look at the PV equals nRT formula, PV equals nRT, if you keep the temperature and volume constant, the moles and pressure are proportional because you can rearrange this equation to get that N is equal to PV over RT. So if you have gas at certain conditions of a pressure and temperature, but they stay constant, okay, then the what happens is as long as the volume and temperature are constant, they aren't going to change. So, and R is not going to change. So basically, N, it doesn't necessarily equal P, but is proportional. For example, if you double N, then you double P. So that's kind of the way you can think of it. You can basically, in other words, you can treat pressure like moles. Okay, so here's an example of what you can do. So if you have 10 atmospheres of O2, you can write that right there, and then you can draw your little picket fence thing, and then you can just look at the formula of O2. So I'm looking at the number of O2s and CO2s, and you can make it proportional. So basically, for every one O2, for every one atmosphere of O2, you can make one atmosphere of CO2 because the two O's go into the CO2s. So it ends up being that you can get 10, that's supposed to be 10, not 1, atmospheres of CO2. Now, if you do the O2 one, it's a little bit different. So let me just show you. If you have 10 atmospheres of O2, all right, so for every 1 atmosphere of O2, you can get, because see, you have 2 O's here and you only need 1 for every H2O, you can get 2 atmospheres of H2O. And so you end up getting 20 atmospheres of H2O. Okay? To make 3 atmospheres of CO2, oops, 3 atmospheres of CO2, how many atmospheres of O2 are required? So we just go like this right here. So basically you just say 1 atmosphere of CO2. There's 2 O's in there. So you can make 1 atmosphere of O2. So the answer is 3 atmospheres O2. Now this one's going to be maybe a little bit trickier, so watch this one. So if you have 3 atmospheres of H2O, how many atmospheres of O2 are required? All right, so for this one, notice that the O2 has more O's than the H2O. So basically, for every 1 atmosphere of O2, you need 2 atmospheres of H2O. And so what will happen is you have to divide that. And so you end up getting 1.5 atmospheres of O2. All right, so that's something to keep in mind. It might come into play sometime. All right, now this is an important thing here. I guess in the equilibrium unit we'll learn how to make ice tables, but this is just kind of it's not technically an ice table probably, but it's just a way to figure out the total pressure in a container. The catch is, in a balanced equation, you can treat the numbers in front like moles. If there's no number, that means 1. So I like to make this thing, I call it an ice table, but let me just draw it right here. And so we have initial, change, and then a lot of times they call this equilibrium, but this really, we're not necessarily doing an equilibrium problem, but we can call it. Basically, you can think of E as at the end of the reaction. All right, so 10 atmospheres of H2, so I'm going to write a 10 under H2, and 8 atmospheres of O2 are placed in a rigid container. After a length of time has passed, a reaction has occurred and some water vapor is formed. Okay, well, we're going to have 0 of this to begin with because the reaction hasn't started. This is initially. Now, as the reaction proceeds, this is going to go down. This one's going to decrease by a value of 2. We don't really know how much. We're going to call that X. This one's going to go down by whatever number that is, down by 1x. This one's going to go up by 2 because I'm using the number right there, 2x. Okay, and some water vapor is formed. The partial pressure of H2 measured in the container is equal to 8 atmospheres. Okay, that's after the reaction has occurred. So we know that this went down to 8. Some of it was used, but not all of it. Okay, but there's 8 left. Okay, so now you can do a math problem and go 10 minus 2x equals 8. You get basically a negative 2x equals negative 2. X is equal to 1. Or you can just eyeball it and say 10 subtract 2 times what equals 8. X is equal to 1. But it's important to figure out that 1 there because you're going to need to use that 1. Once you know what x is equal to 1, you can plug it in over here. And so negative 1 times 1 is negative 1. So 8 minus 1 is 7. And then 1 goes over here. 2 times 1 is 2. But they were adding over here. So at the end of the reaction, oops, that's 4, my bad. 2 times 2, or no, 2 times 1, my bad, 2. All right, not doing the math so good. All right, anyway, so now at the end, these are the pressures in your container. But what's the total pressure in the container? Okay, according to Dalton's law of partial pressures, the total pressure is the sum of the individual pressures. So we would go 8 plus 7 is 15 plus 2. So we're just adding all these together. 8 plus 7 plus 2. That's going to equal 17 atmospheres. Okay, down here, let's do another one here. All right, now this thing I just showed you is useful. You'll see when we do some AP multiple choice problems. Sometimes they give you some things, and you can use this method to figure it out pretty easily. All right, 3 atmospheres of H2 is mixed with 6 atmospheres of I2. Okay, and we're going to say that this is 0. All right. After a period of time, the partial pressure of H2, well, let's figure this out. This is going to go down by 1x. This is going to go down by 1x. This is going to go up by 2x. Okay, where am I getting the 1s and 2s? I'm looking at the numbers in front here. That's going to tell me how much they're going to go up and down by. After a period of time, the partial pressure of H2 is measured at 1 atmosphere. So this is 1 after the reaction is done. Okay, I forgot. I didn't write ice, but whatever. All right, anyway. So 3 minus 1x equals 1. What is x? Well, x has to end up being 2. All right? Because that's kind of, you can tell by how, like, what x is. All right? So 3 minus 1x equals 1. So x is equal to 2. That's something we need to know. So now we can just plug 2 in right here. 6 minus 1 times 2, that's going to equal 4. And 2 times 2 equals 4. So what's the total pressure in the container? The pressure total is going to equal 1 plus 4 plus 4. So that's going to equal 9 atmospheres. Okay, let's see. One more. Okay, so we can just make our ice table. All right, 8 atmospheres of butane. Initial change. Equilibrium. 8 atmospheres of butane is reacted with 10 atmospheres of oxygen to produce CO2 in a rigid container. So initially there's 0 and 0 before the reaction happens. Okay. What is the pressure in the container after the reaction is complete? All right, well, this is going to go down by 2x. This is going to go down by 13x. This is going to go up by 8x. This is going to go up by 10x. Now, one of the things that you got to figure out, this one's a little bit harder, is you got to figure out which one of these is going to be used up first. Okay? Well, basically, for every 2 atmospheres of butane, you need 13 atmospheres of oxygen. Now I can just eyeball it, and we can talk about this later, but I can tell that the oxygen's going to hit 0 first because it takes 13 times as much oxygen as it does this butane. You see, it takes way more than that. So I'm going to put a 0 here. Now what I got to do is I got to do this math problem. I got to figure out what x is. So I'm going to go 10 minus 13x equals 0. Then I move things around, so I get a negative 13x equals 10. Then I'm going to solve for, or negative 10, by the way. So I get x is equal to a negative 10 divided by a negative 13. I don't want to work with a fraction. So I end up getting, let's see, if I take 10 divided by 13, what does that equal? I got to get a calculator out. Let's see, 10 divided by 13. So it looks like that equals around 0.77. So x equals 0.77. Now it's just a matter of plugging in the numbers. So 8 minus 2x, so we got to figure out what 2 times 0.77 is. 2 times 0.77, so that's 1.54. So we're going to be subtracting 1.54 here. And when we do that, we get 6.46. Then we're going to take 8 times 0.77, and that's going to equal, I think, 6.16. Let's see if I don't know if I can do that in my head. Yep, 6.16. So this is 6.16. So we're going to take 0 plus 6.16. And then we're going to get 10 times that. I can do this one in my head for sure. That's going to equal 7.7. Okay, now all we got to do is add up these at the end. So 6.46 plus 0, which we don't need, 6.16 and 7.7. If we add all those up, we get 20.32 atmospheres, or 20.3. I think it's in atmospheres. Okay, that's it on this video. Take a look at those ice tables. They can be tough. You might have to go through this more than once.